The universe is approximately 13.8 billion years old. But if you could look back in time, which forgotten moments of the past would you choose to unfold and observe? Your first day on Earth? Or the Apollo 11 moon landing? Well, let's think bigger. What about the entire history of our universe? The bright seconds after the Big Bang? The evolution of our planet and solar system? In Christmas 2021, NASA, the European Space Agency, and the Canadian Space Agency joined forces to gift the world's astronomers the best present they've ever received. An opportunity to glimpse into the past, at the birth of the universe, and the edge of time itself. This otherworldly window into creation was not revealed by artistic metaphor, a magical time machine or philosophy, but by one of the greatest scientific endeavors of our time. The James Webb Telescope, the premier observatory of the next decade, more commonly referred to as Webb. This enormous infrared telescope began its voyage into the past after launching into space on deck, aiming to capture snapshots of the unknown and reveal the secrets of our hidden universe. How did we get here? Are we alone in the universe? How does the universe work? James Webb is an ambitious scientific endeavor to answer these questions. Up to now, more than 1 year in space, the world's premier space science observatory is truly living up to its bill, solving mysteries in our solar system, looking beyond to distant worlds around other stars, and probing the mysterious structures and origins of our universe and our place in it. Join us as we dig deep into how James Webb just shattered our cosmology into pieces. The universe is a vast place, filled with more galaxies than we've ever been able to count, even in just the portion we've been able to observe. Some 40 years ago, Carl Sagan taught the world that there were hundreds of billions of stars in the Milky Way alone, and perhaps as many as 100 billion galaxies within the observable universe. Although he never said it in his famous television series, Cosmos, the phrase billions and billions has become synonymous with his name, and also with a number of stars we think of as being inherent to each galaxy, as well as the number of galaxies contained within the visible universe. But when it comes to the number of galaxies that are actually out there, we've learned a number of important facts that led us to revise that number upwards, and not just by a little bit. Our most detailed observations of the distant universe, from the Hubble Extreme Deep Field, gave us an estimate of 170 billion galaxies, a theoretical calculation from a few years ago, the first to account for galaxies too small, faint, and distant to be seen. Put the estimate far higher, at 2 trillion. But even that estimate is too low. There ought to be at least 6 trillion, and perhaps more like 20 trillion, galaxies if we're ever able to count them all. But no matter how many galaxies are there in the universe, one thing is for sure: the early universe was vastly different from the one we know today. The Big Bang left the universe in a state of relative simplicity. Our observations of the cosmic microwave background tell us that after the Big Bang, the infant universe was rather uneventful compared to the present. We know that there were no stars or galaxies shortly after the Big Bang. We also know observationally that at the observational limits of Hubble, taking us back 13.4 billion years in time to objects that existed just for 100 million years after the Big Bang, galaxies are already massive, rich in structure, and evolved in terms of the elements that exist within them. Somehow, we have to go from a universe that was born almost perfectly uniform, with the densest regions just a few parts in 100,000 denser than average, to one that's rich in evolved massive galaxies in only a few 100 million years. Unfortunately, we can't simply look for the light that those distant galaxies emit. There's a tremendous difference between the light that a distant galaxy emits and the light that arrives at our eyes after journeying for billions of light years across the universe. That initially emitted light gets affected by everything that interacts with it along its journey, including light-blocking neutral matter, hot gas and plasma that scatters and disperses that light, growing and shrinking clumps of matter that change the gravitational potential in the region where the light is propagating, and the expansion of the universe that stretches the wavelength of any light that travels through it. Even though the laws of physics, from the quantum physics that governs electrons, atoms, and ions to the thermal and stellar physics that govern stars and galaxies, are the same everywhere throughout the universe, objects at different distances won't appear the same way when you observe them. The environments they're in, as well as the environments they must pass through on their way to our eyes and instruments, alter that light irrevocably. If we want to understand and discover what's out there, we need to be able to not only observe the most distant light possible, but to reconstruct what that light was like when it was first emitted so long ago. One of the most suggestive hints you can see that might make you suspect you're seeing something from long ago and far away is simply based on the color of what you're looking at. Stars, by and large, emit light from the ultraviolet through the visible and into the infrared portion of the spectrum. When you see an object that's redder in color than the typical nearby objects we observe in our vicinity, there are many possible reasons why it might appear red. It could be full of intrinsically red stars. It could be extremely dusty, where light-blocking material obscures the shorter wavelength light. But one fascinating possibility that must be considered is that it's red because the expansion of the universe shifted that light, emitted at much shorter wavelengths, to the long wavelengths we now observe. One of the keys to unlocking our understanding of our cosmos, as well as our place within it, came about in the 20th century when we discovered the expansion of the universe. The fabric of space itself is like a ball of leavening dough, and the galaxies within it are like raisins sprinkled throughout it. As dough leavens, it expands, and all of the raisins mutually get farther apart from one another. From the perspective of any individual raisin, or of any observer located within a galaxy, the other raisins, galaxies, move away from it with more distant raisins, galaxies receding more quickly, and the light traveling from one to the other experiencing a greater shift in its wavelength, the ones found more nearby. You can't simply detect light of any arbitrary wavelength with any old telescope, detector, or observatory. Longer, redder wavelength light corresponds to lower energies and cooler temperatures. And if you want to detect it, your telescope and its instruments must be cold enough so that the low-energy light you're seeking to detect is the signal that can rise above all forms of noise that would be present. While Hubble can see light out to a wavelength of about 1.5 microns, James Webb is cold enough to see light up to 20 times longer in wavelength, all the way out to 30 microns in wavelength. Only because of its cold, cryogenic, pristine properties can it see the reddest, most distant objects of all. Custom, made to find and study the very first galaxies, James Webb's unprecedentedly powerful infrared gaze is already delivering insights from across cosmic history, whether concerning the early evolution of the universe or the atmospheric chemistry of nearby exoplanets. Given its presently unparalleled capabilities and its price tag of more than $10 billion, some might consider the Webb telescope the one telescope to rule them all, the greatest and last orbital observatory we'll ever really need. Having said that, the first year of the James Webb Space Telescope has been a big success, exceeding expectations. According to NASA, it has provided astronomers and scientists with amazing pictures and data to study. It has changed our understanding of the universe and allowed scientists to explore distant places in unimaginable ways. The journey of the James Webb Space Telescope began with its first pictures of thousands of galaxies in a group called SMACS 0723. Since then, it has captured breathtaking pictures of galaxies like the colorful hills in the NGC 3324 star region. It has also studied the 5 galaxies of Stephan's Quintet and the Southern Ring Nebula. Additionally, it has studied the atmospheres of planets outside our solar system, such as WASP 96b. Some trouble lies where James Webb is now breaking observational records previously thought unreachable. The distant universe where its quarry of firstborn stars and galaxies dwell. Webb's deepest, Farthest, seeing images are revealing unexpectedly large numbers of galaxies so big and bright they defy easy understanding. Explaining how they came to be could lead to major revisions to our models of the early cosmos, and to our knowledge of the fundamental physical laws such models encapsulate. For instance, consider the case of GN Z11, first glimpsed by James Webb's predecessor, the Hubble Space Telescope. This is a galaxy that is among the earliest and most distant ever seen. To date, the Webb telescope has spent at least 20 hours closely studying GN Z11, a heavy investment of the telescope's precious observing time, yet one that still leaves open whether this faraway galaxy possesses a central supermassive black hole. Such black holes, which Hubble found lurking in most large galaxies it observed closer to us in the universe, pose a chicken and egg problem for cosmologists. Which came first, the giant black holes, or the galaxies they occupy? Solving that mystery could reveal how the very first black holes and galaxies were born after the Big Bang. Astrophysics thrives when astronomers can synergistically use multiple telescopes operating across a wide range of the electromagnetic spectrum. Time and again, this broadband view has been essential for learning the true nature of mysterious objects in the heavens. To gain a better picture of the population of black holes in the universe, what's needed now are X-ray observations. Although not as sublime as their optical counterparts, X-ray images reveal the most extreme cosmic events, such as a supermassive black hole feasting on galactic volumes of gas and dust, which emit lots of energetic X-rays. Detecting even a few stray X-ray photons from GN Z11 or one of its kin would strongly suggest the presence of a supermassive black hole there, providing invaluable data points for the timing and mechanics of cosmic evolution. But no facility yet exists to perform these demanding observations. The current major X-ray telescopes, Chandra and XMM Newton, have both significantly degraded since being launched more than 20 years ago, and neither is sensitive enough to detect black holes smaller than about 1 million solar masses in the remote cosmic regions that James Webb is exploring. Without a more powerful state-of-the-art X-ray observatory, we may miss our chance to understand how black holes evolved in space and time, an enigma revealed by successive generations of humankind's best, most cherished space telescopes. This helps explain why many astronomers are now already looking beyond James Webb and its forecast 20-year lifetime to envision an ambitious series of new great observatories, each sensitive to a different type of light. Ideally, all would have to be launched in relatively rapid succession around the time Webb's mission ends, maximizing scientific return via their overlapping operational timeframes. The original Great Observatories program debuted in 1990 with NASA's launch of Hubble and included Chandra and 2 additional now defunct space telescopes, the last of which was sent to orbit in 2003. As recommended in 2020, one by the congressionally mandated Decadal Survey of U.S. Astronomers, this plan calls for a trio of new space observatories. The first, now named the Habitable Worlds Observatory, would launch in the early 2040s to study potentially Earth-like exoplanets, and much, much more in optical, ultraviolet, and infrared light. The other 2, one for X-rays, another for far infrared, could launch later that decade or in the 2050s. Together, they could create a profoundly informative, more colorful view of the universe, ushering in a new golden age of space-based astronomy about half a century after Hubble's launch. The proposed X-ray observatory, for example, could detect growing black holes as small as 10,000 solar masses within the mysterious early galaxies seen by the Webb telescope. A factor of 100 improvement over Chandra's capabilities. However, whether through wavering political support, unanticipated technological challenges, or merely the harsh realities of NASA's overloaded portfolio, there is a good chance these decadal plans will not proceed at their optimal speed. A slower pace of development and funding could result in longer lag times between launches for the 3 new great observatories, reducing the likelihood that they will operate concurrently, as well as their overall scientific return. According to one analysis, having all three facilities operational by 2045 would require doubling NASA's astrophysics budget through the remainder of the 2020s and into the 2030s. Currently, there's as much evidence for such an increase becoming a reality as there are X-ray photons from these faraway galaxies. None. Far from doubling down on funds, the administration's latest budget proposes an increase in spending of only 3% for NASA's astrophysics division in the 2024 fiscal year. With its successive multi-billion-dollar investments in James Webb, Hubble and their telescopic kin, the U.S. and its international partners sparked an ongoing scientific revolution, representing humankind's best hope of learning our deepest origins, context, and fate. Fulfilling that profound potential and maintaining leadership in space science demands strong, sustained support for the next generation of observatories. Otherwise, we may fail to fully answer not only the current set of open questions, but any new ones that arise in our epochal quest for cosmic understanding. While we wait for the launch of future space conquerors, continue to admire the sharpest ever photos of the universe taken by James Webb. The world's premier space science observatory continues to give us cosmic eye candy, this time while shedding light on the cosmic noon. The newly released James Webb Space Telescope photo captures NGC 346, a star-forming region in a satellite galaxy of the Milky Way called the Small Magellanic Cloud. The blue wisps of light represent emissions from molecules like silicates and polycyclic aromatic hydrocarbons, while red fragments highlight dust warmed by the brightest and most massive stars in the region's center. Overall, astronomers have detected 1001 light dots in the image, and most of them are still young stars blanketed in dust, according to a statement accompanying the image. This pocket of the universe is much younger than the Milky Way, our home galaxy, which is seen in the fewer amounts of heavy elements it features. The intriguing region is visible to the unaided eye in the southern constellation Tucana. Heavy metals are usually churned in stars across time spans of eons, then deposited back into their local surroundings via cosmic processes like nuclear fusion and supernova explosions. Astronomers know cosmic dust is formed from those heavy elements, so they expected to see little of it in the NGC 346 region. However, the latest photo shows ample dust within this region, Webb representatives wrote in the statement. Astronomers say the image, which was captured using the mid-infrared instrument MIRI onboard Webb, is allowing them to better understand how many stars and protostars are present in the region. Those observations could eventually shed more light on an era in the universe billions of years ago known as cosmic noon. At that time, star births reached a peak rate across the universe, and the level of heavy elements was lower than amounts measured today. A distribution in line with how NGC 346 is now evidenced to be. In addition, NASA's James Webb Space Telescope also has just taken a closer look at a volatile star at the heart of a system of 7 potentially Earth-like worlds, some of which might be able to support life as we know it. The powerful space telescope studied 4 flares erupting from the star TRAPPIST. 1, a cool red dwarf that's located about 41 light-years from Earth in the constellation Leo. Researchers decrypted the flare's radiation from the star's regular light, something that could aid the hunt for habitable conditions in this extraordinary system. Because of the James Webb Space Telescope, it is the first time in history that we've been able to look for planets around other stars that have the sorts of secondary atmospheres you could find around, say, Earth, Venus, or Mars. Research lead author Ward Howard, a NASA Sagan Fellow at the University of Colorado, Boulder, said in a statement, "If we want to learn more about exoplanets, it's really important to understand their stars. Red dwarfs like the Jupiter-sized TRAPPIST, 1, which has a mass around 9s that of the Sun, are the most common stars in the Milky Way, and despite their small stature, are also the most active. TRAPPIST, 1 emits powerful blasts of energy as flares several times a day. Our own Sun, by contrast, erupts with similar outbursts just once a month or so. The violent activity of red dwarfs makes studying the atmospheres of their exoplanets a challenge. Astronomers study alien atmospheres by observing light as it passes through them, and chaotic emissions of stellar radiation complicate this process. Howard and his colleagues addressed this challenge by observing flares emerging from TRAPPIST, one over a period of roughly 27 hours. They then separated these bursts of light from the regular light coming from the star, filtering out around 80 of the flare-based radiation. If you don't account for flares, you could detect molecules in the atmosphere that aren't really there or get the amount of material in the atmosphere wrong, Howard explained. Additionally, not only was the team able to observe a stellar flare in certain wavelengths of infrared light for the first time with the Webb telescope, but they also captured the evolution of those 4 flares in detail, watching over several hours as they grew in brightness before peaking and becoming dim again. This method could be key for obtaining clearer images of planetary atmospheres and will likely be applied to the TRAPPIST-1 system in particular. In case there are someone wonder what makes TRAPPIST-1 a prime target for scientists, we also get the answer. TRAPPIST-1 has been a tantalizing target for astronomers since 3 planets were first discovered around the red dwarf star in 2016. The fascination with the system in the astronomical community intensified with the discovery of a further 4 planets around the red dwarf star. Itself discovered in 1999, not only do these planets seem to be rocky like Earth, but 3 of them exist in the habitable zone of TRAPPIST-1, the region in which it is neither too hot nor cold to allow water to exist as a liquid on a world's surface. A vital condition for life as we know it. The James Webb Space Telescope is already starting to investigate the atmospheres of the TRAPPIST-1 worlds. A recent study of one of those planets, TRAPPIST-1b, revealed that it seems to lack an atmosphere. This new breakthrough should allow astronomers to get an even clearer picture of the conditions around the planets of this fascinating system. With TRAPPIST-1, we have a really great opportunity to see what an Earth-sized planet around a red dwarf would look like. There are only a handful of stellar systems where we have the opportunity to look for these sorts of atmospheres. Each one of these planets is truly precious. The team's research has been accepted for publication in the Astrophysical Journal, and a preprint version is posted on the paper repository Arxivory. After all, it could be said that the James Webb Space Telescope has ushered in a new era of science, and despite the uncertainties, the rapid communication of new discoveries has invigorated astronomers. As Webb Senior Project Scientist Jane Rigby of NASA's Goddard Space Flight Center said, "With a year of science under our belts, we know exactly how powerful this telescope is and have delivered a year of spectacular data and discoveries. We've selected an ambitious set of observations for year 2 that builds on everything we've learned so far. Webb's science mission is just getting started. There's so much more to come." That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.